Okay, so recording has started. So this is the first lecture after midsem. I hope your midsem was fine, and your question paper, if your answer script are now we are checking the answer script. Most probably by this weekend, my TAs will share all the answer script with you, also along with the key answer of all the questions. After that, once the TAs will explain everything, then you'll see your marks, and after that, if you have any confusion, then you can discuss with the TAs. Even after discussing with TAs, and if you feel that you are not satisfied, then only you can discuss with me. So first is, if you think that there is any confusion, or you should get more marks and all, first discuss with the TAs, and then even if after that or you are not satisfied, then you can discuss with me also. And regarding your, I think both the class tests, I think two short quizzes are remaining for, I have not given marks for them, so that those marks will be uploaded also by this weekend. And from today, this since this is the first lecture after midsem, so what I'll do, uh, I'll start a new area today, new section today. Maybe my screen is visible. My screen is visible. Can
Yes,
you
sir.
see the screen?
Yes, sir.
Okay, nice. Okay, so if you see, we have started from this book. So we started from chapter one, then chapter two, and then chapter four. So chapter one, two, and four are mostly covered before midsem. So there are some section. One important section remains from chapter four, that is branch prediction, that I'll discuss after the memory. So from today's lecture, I'll start explaining you the memory, computer memory. So memory hierarchy. So this is actually chapter 5 of this book. So memory hierarchy. So in next 2-3 weeks, we'll discuss the concept of memory completely. You'll understand and after that, we'll also understand the recent advancement that is going on memory. And there is a project that you need to do. If you remember the first lecture, I have mentioned that after the midsem, you will do a project. So that project I will discuss after 1 week. So maybe by the end of today is Thursday. By next Thursday or by next Friday, I'll give you the project detail. So before giving you the project detail, I need to explain some concept of memory, because the project that I'll give you, it will be based on memory. And for that project, you need the knowledge of C++. Okay, so I think at the beginning of this, I've taken some lectures which are not connected with this book, and in that, one of that lecture was based on memory. And in that lecture, I've explained you the memory hierarchies, that then fast code, then registers, then cache memory, then main memory, and then the hard disk. So now I think after spending all the time on assembly language and all, now I think you have an idea what is called register, at least, right? And if you remember the data path, then the data path has two boxes, right? One is for instruction memory and one is for data memory. These are actually the cache memories. These are called L1 cache memory. One is actually L1 instruction cache, and another we call it L1 data cache. Okay, so I'll since I have explained most of the basic concept of this chapter already, so I'll just quickly scroll it, and if I found anything new, that I'll explain. So my advice will be, watch the initial lectures where I've explained the concept of memory. Those will be required here, because I'll not explain all the concept again here, because many important concept of cache memory I've already explained. So if I scroll this book first. Why I'm scrolling this book, because I'm expecting that you will read it. That's why, because maybe the concept I'm explaining, but when you read the book, you will find some interesting points also. So here, this concept of temporal locality and spatial locality I've already explained. So I'm not explaining it again. So that's why I'm saying, please watch the lecture that I've covered first. Otherwise, you may face some difficulty to understanding whatever I'm saying. So this is memory hierarchy. In memory hierarchy, this is a diagram that is shown. See, there are first processor, and if there are some registers, then those registers will be inside the processor. Then after the processor, the next memory is designed. This is the next memory. This we can say cache. So this is actually the processor. Okay, and then this is actually the RAM that we call RAM or main memory, and this is the HDD, hard disk or SSD. And now you can see the size. Cache memory is the smallest memory, then and the SSD or HDD hard disk are the largest memory, and RAM is the intermediate memory. Cost wise, cache is the costliest memory, and the cost of HDD hard disk or SSD is the lowest compared to all these three types of memory. Current technology is cache memories are designed with SRAM technology, and mostly, I'll say mostly, because at the end of this course I'll explain you that no, the only SRAM technology is not the SRAM technology is not the only technology that people are currently using for cache memory. But at the beginning of the memory concept, let us just understand that cache memories are designed with SRAM technology, and main memories are designed with DRAM technologies, and hard disks are mainly designed with magnetic technologies, and SSDs have different technologies. They are mainly with flash technology. So all the technologies I'll discuss today, but also I'll quickly go through this technology again. So this is how this is the memory hierarchy here. I hope you will you remember this memory hierarchies and why we use cache memory. That if the processor requests for a particular word, or then first you'll search in the cache memory. If the block is found in cache memory, then it is called a cache hit. So the data will be returned from the cache to the processor. When it happens twice, right? First, to fetch an instruction. When we fetch an instruction, then we have to go to the instruction memory. That is actually L1 instruction cache. This is the first instance. Another two instances are for load and store. If it is a load and store instruction, then we need to access memory, right? In memory access, we need to go to L1 data cache. So when every time when we say the processor is requesting for a block, so what is this? Processor is either requesting for an instruction, that is the instruction fetch time, or the processor may be requesting for a data block during the mem stage of load and store. Okay, so here processor is requesting for the block if they or a word. If the word is not here, then it's called cache hit. So it will be supplied directly from memory, from cache memory. If it is not here, if the cache means, then you have to go to main memory, and from main memory the first block will be moved to this cache memory, and from cache memory it will go to the processor. And if it is not in the main memory, then we'll normally go to SDD. But that is a different concept, and that I'll not discuss here, because this concept needs some understanding of page fault and all. So I'll discuss it at the end of this chapter when I'll discuss virtual memory. So now from this at this moment, we'll only concentrate up to this level, that if there is a miss in cache, we'll go to main memory, and from main memory we'll fetch the data. At this moment, we'll assume that every data is available in main memory. Okay, so let us just scroll down. If you scroll down here, then there is a diagram here. I will not explain this diagram here. This, I think you will understand it. This is not a very important diagram. After this, you will find some definition here: hit rate and miss rate. So I have already explained you that if there is a hit, and if you find a block in the cache, that is called cache hit, and if you don't find a block in the cache, then it's called cache miss. So I hope you are understanding the difference. If it is a cache hit, then if there is a cache hit and if the time taken is X, then if there is a cache miss, then the time it will take to fetch the data from next level of memory, that is main memory, will be at least 100 of X. So now you will understand what is the importance of cache hit. So what is called hit rate? Hit rate is hit per memory access. That is called, so the fraction of memory access found in a level of the fraction of memory access is found in a level of memory hierarchy. So if I say hit rate of cache, then it means that hit in cache per memory access. So same if you go over miss rate of cache memory, then it means the number of misses per memory access in the cache memory. So hit rate and miss rate are clear. Hit time is time. If there is a hit in the cache, then time to access the cache to fetch the block. That is called hit time. So if you have, this is your cache memory, and processor is requesting for a data. The data is in the cache, but if the data is in the cache, then also you need some time to access the data from the cache. So that is called hit time. And if the block is not in the cache, then you have to go to main memory to fetch the data, right? So in that case, this time is called miss penalty. Means if there is a miss in this cache, then you will go to main memory, and from main memory you will fetch the data. So this time is called miss penalty. This time is called miss penalty. Okay. So hit time and miss penalty definition is here. You should understand what is hit time, what is miss penalty. This definition will be required. So I'm quickly scrolling this. This is a simple diagram. Again, you will understand it. Level 1, level 2, level 3. This is the memory hierarchies that I've explained. And then coming to this memory technologies, this part, the memory technology means how the memory are designed. So I think this before midsem, I think I have uploaded one extra lecture on DRAM technologies. So that extra lecture will be now a compulsory lecture after midsem. So I'll again share that lecture as a compulsory lecture. There are some advanced material in this lecture, but still I'll consider this as a compulsory lecture of this for this course, because if you watch that video, then you'll understand different techniques of different memory technologies very properly. In fact, I'll upload I think two lectures on memory technologies. Those are already recorded. I'll just upload them. So no need to worry. Now you no need to think that which extra lecture is important. Extra lectures are extra lectures. Now, if any lecture I'll consider as a main lecture, core lecture for this course, then I'll upload that lecture again. So no need to take any tension at this moment. Okay, so memory technologies means how to store memory, right? Because if the concept that we know from our what you could say memory card that we use in our mobile phone, right? Pen drive, what this all are memory devices, right? Considering cache memory, RAM, all are memory devices. So we normally use them to store memory. But in computer, we understand that every information that we store in computer is form of binary, right? It's a string of zeros and one, zero, one, one, zero, zero. So ultimately, if you want to design a memory, then the main important thing is how you will store one bit of information, right? How you store binary zero, how you store binary one. If you can store binary zero and binary one, if you have two techniques, then you just replicate these two techniques, and you can store any combination of zero and one, right? So the memory technology means the technology used to store one bit of information. Okay, so you can see there are some memory technologies here: SRAM technology, DRAM technology, flash technology, magnetic disk technology. These are different technologies using which you can store one bit of information. Now the next question is, why so many technologies? Their behavior is different. If you go for SRAM technology, then it is very fast. It means if you design a memory, suppose this is a memory of SRAM using you have designed with SRAM technology, then accessing this memory will be very fast. You can see the typical access time here. You can just compare the access time of memory designed with SRAM and the uh, and the memory designed with DRAM. Suppose there is a same memory here designed with DRAM. So you can see the access time. SRAM memory is much faster to access as compared to a memory designed with DRAM technology. But if you go with cost wise, then SRAM designing a memory with SRAM is very costly compared to DRAM. See, you can see the difference, right? Same thing you can see here for flash memory and magnetic disk. But I'll discuss the last two after discussing the first two, SRAM and DRAM. Why SRAM and DRAM? So just I said that normally we use SRAM to design cache memory, and we use DRAM to design main memory, or that we call SRAM, right? It is main memory. Okay, so why cache is designed with SRAM? Because we want a faster memory in cache, because cache is very near to the processor, so we need a faster memory, small but faster memory. That's why SRAM is used for cache. And why we don't use SRAM for designing DRAM? Because DRAM are normally larger memories. In modern desktop nowadays, 8 GB, 16 GB, even 32 GB of RAM is also common, even in a normal desktop machine, right, or a laptop machine. So designing this type of huge memory using SRAM will be very expensive. That's why we normally go with DRAM technology to design the main memories. So these are the two difference. And since main memory is an off-chip memory, I hope you're understanding what is called off-chip. It is outside the processor, right? So since it is outside the processor, it's the off-chip memory. So here latency is not much important. Here capacity is more important. That's why here our goal is to design a larger memory, By designing this, if we can compromise some with some latency, then also fine. That's why DRAM is a better technology for RAM or main memory. But in case of cache, we need a small but faster memory, because if the cache memory is small slow, then what will happen, you can understand. If you remember the data path that I have that we use in data path during this mem stage, if when it is going to access a memory, if that data memory is designed with DRAM cache and it is taking long time, then what will happen? Ultimately your cycle time will increase, right? Or you should go for multiple cycle. If you for example, what we assume during pipelining, then every stage will take one cycle, right? And here, if you think that instead of the data memory is of DRAM, then what you have to do, there are two options. Either you have to extend the cycle time, right? Or you can say that no, the mem stage will require multiple cycle. So both will cause performance degradation. That's why SRAM is a better idea to go with cache memories. So this I'll not discuss the internal technology more, but two more interesting thing I'll say. As I said, both SRAM and DRAM are the technology to store 1 bit of information, right? So in SRAM, if you want to store 1 bit of information, you need 6 transistors. I think 6 to 8 transistors are required in SRAM to store 1 bit of information. But in DRAM, if you want to store 1 bit of information, you need only one transistor and one capacitor. Here there will be a capacitor like this, and if the capacitor is fully charged, then it is means suppose it's considered as binary 1, and if the capacitor is not charged, then we'll call it as a binary 0, and there will be a transistor connect here, though that transistor will connect to this capacitor to read or sense this charge. I think the video that I've shared of DRAM explain all these things. Okay, so advantage here in there is the advantage of DRAM also. DRAM is there are less density. Density means suppose this is the chip area. This chip area is fixed. Within this chip area only you can place a memory. So if within this chip area, if you can place only a 4 MB of SRAM cache, then within the same chip area you can place at least 40 MB of DRAM cache or DRAM memory. Why? Because here to store 1 bit of information, you need only one transistor and a tiny capacitor. But if you go to SRAM, you need 6 to 8 transistors. So density is very less here. It is an area consuming memory technology. And here density is very high, and it is so you can place more memory storage in a small chip area. So these are some differences. When you read this section, you'll understand it. And so here there is a difference between the first two technique and the last two technique. The first two techniques are called volatile memory. Volatile memory means if both in SRAM and DRAM, if you switch off your power, then the data that is stored in this memory will be vanished, right? Because these are called volatile memories. But the last two here are called non-volatile memories. It's like, for example, a pen drive. If you store some data in pen drive, even if you remove it, or if you switch off your computer, you remove the pen drive, you move it to some other place, the data is still there, right? So this is called non-volatile memory. The same is true for your hard disk or SSDs also. When we shut down our computer, and if we start it again after 1 week, our data will be remain there, right? So that's why the remaining two here, first two are volatile, next two are called non-volatile memory technologies. So there are the other memory, non-volatile memory technologies also exist. So as I said, I'll share one interesting video on different non-volatile memory technologies, and those will be a part of your this course. These videos are already uploaded as an extra lecture, but I'll re-upload them, and now I'll make them compulsory for this course. Yes, there will be some advanced level concept, but those will be helpful for you to understand the memory technologies. So now from this point onwards, my only intention, there are two intentions now from my side. One is to explain you the concept of memory. Whatever written in book, obviously will explain. I'll explain you the concept of memory. On top of that, there is a secondary motive also from this point. My secondary motive is to motivate you to work in this area, to motivate you to do further research in computer memory. I'll try to motivate you. I'll explain you that, see, what are the recent advancements going on, what are the new, what are the challenges still exist, and in which how you can contribute in this area, what are the new research that you can do in this area. So all these interesting points we'll discuss from in this post midsem lectures, and I hope some of you will be interested to do further work in this area. Okay, so DRAM technology, I'm not explaining it here, and I will advise you to watch the DRAM video that I have already uploaded, or I'll share just after this lecture again. So watch that main memory technology wala video, and then you read this section, then it will be easy for you to understand. If you read it fast, then you no need to read these sections from the book first. Just watch my video first and then go with this section. Then flash memory, disk memory, and all. So disk memory is normally they're explaining here how the hard disk are designed. So in this course I'll ignore this section, so you can also ignore the disk memory details. These are also interesting, but I'm not covering it here in detail. Okay, then basics of caches. So far I have explained you what is cache memory, what is memory hierarchy, right? What is cache hit, what is cache miss, hit rate, miss rate, then hit time, miss penalty. All this concept I've explained. Then I've explained you that the memory technology is used for as cache memory, then main memory, then hard disk, difference between volatile memory, non-volatile memory. All these things I've explained. And also I've mentioned that if you want to know more about this, then I'll share some lecture videos. Watch first those lecture videos first, and then read this book. Now the basics of cache. Basics of cache, again, I will not discuss much here because I think basics of cache memory I've already explained at the beginning of this course. So you also need to watch those videos. So if I remember before midsem, I've only explained you a special kind of cache memory that is called set associative cache. But today I'll not start with set associative cache. In this section, if you see here cache memory, first they have explained a direct map cache, basics of cache memory. So assume that cache memory is a direct map cache. Direct map cache means, suppose cache memory, this is the cache memory, this is the cache memory, this is the cache memory. So here I'll consider these as set, the columns I'll consider as set, and this I'll consider as way. Sorry, the rows I'll consider as set, and columns I'll consider as way. So there are how many sets are here? 0 1 sorry 0 1 2 3 4 5 6 and 7. So there are 8 sets here. Index will start from 0. Okay, so and in each location here we can store a block. Here there will be a block will be stored, block 1, block 2. In every location we can store a block. Now the question is, sir, what is block? I think the concept of block I've explained before midsem, but I'll quickly explain it now again because I think this is very important concept. So I'll go here and I'll explain you block again. So before understanding block, let me design a memory here. Suppose this is a memory, very big memory, suppose, and suppose the address is starting from 2000, and suppose it is going till 4000 plus something. And this is a byte addressable memory. Byte addressable memory means every byte has an address. So suppose this is 2000, then this is 2001, 2002, then this is 2004. So suppose 2004. So this is called an word. Suppose this is word 1, right? Because we said a word normally consists of 4 bytes. So 4 byte means what? So the address of first word will be 2000. The second word is starting from 2004, and it will goes till 2007. So at 2008 here, the third word will start, and this will go till here. So this is word 2, this is word 3, and maybe at 2012 the fourth word will start like this. So now what will be the address? Address is, suppose we'll go w1, word 1 address is 2000, word 2 address will be 2004, word 3 address is 2008, and word 4 address is 2012. Okay, and now suppose these are called words. So if there is a core here, this is the core, suppose C1. As I said, core request for a word or double word. Here I will consider a word. So core will either request for W1, W2, W3, or maybe then after this there will be one more word here, right? W5, then W6 will be here, W7, W8. There will be multiple words here, right? So a core will request for a particular word at a time. So maybe when it will request for W4, then it will request for this address 2012. This it will request for this address. Core will request for this address. It will always request for a word. Now, what we do actually in cache memory? So this is, suppose this is your main memory. So when core will request for a word, suppose core request for a word called word 2. Okay, so when so suppose this is your cache memory, and the block is not in cache now, because in the first time there will be miss, so the w2 is not in the cache, so we'll go to main memory to fetch the block. So when we go to main memory to fetch the block, we'll not just fetch w2. With w2 will fetch it will fetch an entire block, not just a word. So block contains multiple words. So let us go and understand the concept of block, though I have already explained it, so I'll explain it again. So assume that my block size is of 16 byte. If the block size is 16 byte, then how many words is possible inside it? One word is of 4 byte, right? So 4 words will be there in one block. So suppose this is one block, this is block one. Similarly there, this will be uh, this will be block 2, right? This, so it is block 1, block 2. Similarly there will be block 3 here, right? So when the core will request for a word, but when it will go to main memory, instead of just sending w2, it will send the entire block b1, and b1 will be placed here. So that's why I said, when I said about direct map cache, so you can consider this as a direct map cache. This cache is a direct map cache. So this side, these are sets, and columns are called ways, right? So as I said, in every position you can store one block here. So you can see here in set number 0, I have stored b1. Okay, so now I hope you are understanding the concept of block and what now, but still some more things need to discuss here. So what will be the address of b1? Address of b1. So let us now write the address of b1. Block 1, what will be the address of block 1? 2000. Okay, what will be the address of b2? From where b2 is starting? B2 is starting from this point, and this is actually 20. The byte address here is 2016. So address of b2 will be 2016. Similarly, the b3 is starting from 2032. So b3 will be 2032. In this way the blocks. So I hope you are understanding that. You can see all w1, w2, w3, w4, these 4 words are from block 1. Okay, so you have to understand that underlying memory is byte addressable. This is the first point. Then the bytes are divided into words. Each word has an address, but at the, it's not like there's the word number 1 will be address like 2000, so next word will be 2001. It's not like this. Address will be still maintained based on byte. So if the first address of w1 is 2000, the second address of the second word will be 2004, not 2001. Address will be always byte addressable. You have to understand that. In this way, now you are understanding what is called block address, what is called word address and all. Now suppose if the processor is requesting for a word called w2, how will understand that w2 belongs to block 1, not block 2? Is it very tough? So how normally we do? Normally it is very simple. How? Because of this we will understand that how many uh, bytes are there within a particular block. So as I said, there are 16 bytes here, right? And each byte is a addressable. So as I said, byte addressable. So how many bits are required for this to uniquely identify each byte? 4 bits, right? Because there are so my question is, how many bits are required to uniquely identify the bytes within a block? So how many bytes are there within a block? 16 bytes are there, right? 16 bytes. So 4 bits are required, right? 4 bits are required to uniquely identify a particular byte inside the block. So it means that whenever core will request for a block w2, so we know the address of w2 is 2 is 2004. This is the address of w2. Let us, if you convert this to binary, then what you need to check only that the last 4 should be 00, and these remaining bits are not important. Okay, so these bits these bits are important, so these bits will be the block address, and the first 4 will be always 000. So this will be the block address. So any block address here, b1, b2, b3, any block address here, this part will be vary, but last 4 bit will be always 0000. So it will be very easy to, it is very easy to find out the block address, because we know, and this part is called block offset. Actually this part is called block offset. So it is very easy to find out a block address from a word, or from a word address. We'll just, what we'll do, we'll just make the first 4 bit as 000, and that will be the block address. Okay. And when there is a, so when the core will request for a word, but here we'll search for a block. If the block is not here, then we'll go to main memory, we'll fetch the block here. And after fetching the block here, then the part our W is within the block, right? So after that, the W will, 2 will be sent to this core again. So I hope this concept, the concept of block, what, and or what is called offset, and why the block address must be all 00, why these 4 bits are required for offset, all this concept must be clear. If any of this point is not clear, then you can ask questions now, or you can also ask me later. Okay, so direct map, coming back to direct map cache again. So this, I said that rows I'll consider as set, and columns I'll consider as weight. I think, if you read the book, in book it is given written as opposite way. In this book they said that uh, they said rows as ways, and column as set, but I'll not follow this. So you have to understand that for the rest of the discussion here post midsem, I'll consider this row as set and column as way. So they have explained direct map cache. I think I've already explained direct map cache here. So you can see that so direct map cache I've explained, but how we'll map the data in direct map cache, that I'll explain again. So suppose you have a 64-bit address. So first few bits will be for offset, that I've already explained you, right? So if your say the block address or block size is 16 byte, then there will be 4 bits here, right? These 4 bits will be required for these 4 bits will be required for your block offset. And then the number of set, how many number of set here, there are, you can see there are 8 sets, so you need a 3 bits here for set index. I'll explain why. And remaining bits are called tag, and this is called set index. If I go back here and I'll expand it again, then what I have explained here, that this is your cache memory, right? Assume that there are eight sets here. In this there are 8 sets, okay? And block size, I said 16 byte, right? Block size 16 byte. So if block size is 16 byte, then what will be the offset? Offset will be 4-bit, right? Because block size means inside the block there are 16 bytes, right? There are 16 byte inside the block. And if it is a byte addressable memory, then how many bits are required to uniquely identify a bit? 4 bits are required, right? That's why offset is 4. So if I go back here to address divider, so, and what is this entire box here? The bigger box here is the address. So here I say 2000, 2016, 2032, these are actually address. So normally we consider either 32-bit address or 64-bit address. If we consider here, we'll consider here 64-bit address. Address means every memory has an address, right? So here we'll consider it as 64-bit address. So this is the complete 64-bit is now divided into 3 parts. You can say first part is offset. Here it is 4-bit. Why it is 4-bit? Because we are assuming here block size is 16 byte. And then there are 3 bits here for set index. Why 3 bits? Because if you see the direct map cache that I'm assuming here, there are 8 sets. So 3 bits is required for set index, and the remaining we'll consider as tag. Okay. Now the next is mapping. Why we are going for set index? We are going for set index because every time there is a requesting for a core is requesting for a block. So one more assumption I'll take. See, if I go again here in this, I say core is requesting for a word, right? You can see core C1 is requesting for W2. But after W2, when we'll come to cache memory, we'll not search for W2, we'll search for the entire block, right? Block that is called B1. So now when code is, so that's why instead of saying that code is requesting for a word, sometime I may also say that code is requesting for a block. But you have to understand, code is requesting for a block means code never requests for a block. Code requests for a word only. But I'm saying about the block where the word belongs. Okay. So now when code requests for a word, then or code requests for a block, then that block has an address, right? So that address is suppose this is a 64-bit address. Obviously, if we say about block, then these bits will be 000. This is offset bit, and after this there are the remaining 3 bits here. These are called set index bit. So based on these 3 bit, we will decide that which set this block will be mapped. Suppose in this 3 bit it is written as 0, 001. So it means that this block will always map to set number 1 here in this set. It will never map to any other set. That you have to understand. So that's why every block based on its address, it will map to a particular location of this cache. It's not possible that you'll fetch the block and wherever that memory is free in the cache, you can place it. It's not like this. Suppose there are 3 blocks, B1, B2, B3, and B4. Suppose there are 4 blocks. So assume that all these 4 blocks somehow, mapping to same set number 1. So what will happen if first time you fetch B1, then B1 will be here. After that, if you want to fetch B2, though there are free space available in the cache, you cannot map B2 in any other set because they are mapping in the same set. So you have to remove B1, and in this place you have to store B2. That you have to understand. That is called mapping policy, and mapping policy depends on your set index. This 3 bits here, this 3 bits is called set index. So set index is very important. So now I hope this point is clear, but now I'll explain you this mapping policy without set index. That is also very simple to understand. Because why it is easy, because if you see here that there are 8 sets, right? And each set there is only one way. So in each set you can store only one block, right? You cannot store 2 blocks in one set, right? So if you have 8 blocks here, and so how can you map it? If you know the block address, then you can perform this operation. I think they have written this operation. Yeah, if you have the block address, then block address modulo the number of block in the cache. If you do this, then also you'll get the same thing, same set number you will get. So this is the same operation, so I'll not explain it more in much detail. You can also understand it. Suppose if you the code is, suppose code is requesting for W2, right? As I said, W2 address is 20004, right? To 2004. If this is the address of W2, but from this word address you can find out the block address is 200, right? This is the block address. So if this is the block address, then you divide this block address with the number of cache block available. Number of cache block available is suppose 8, and then take the result here. So based on this you can find out the set index easily. So what we are doing here is exactly same that we have done. That first you remove the offset part, because if you make everything 00 in the offset part, then that will become the block address. Okay, that will become the block, and then you take the next 3 bits, because here there are only 8 sets. So take the next 3 bit, and based on this 3 bit you decide the set index. The same thing they have explained here also, but it will be better if you understand it in the way that I've explained: offset, set index, and tag. Because when you'll go with other cache memory, that is set associative cache or fully associative cache, then that will be easy for you to understand. So now if we go to this diagram, you can see, suppose this is same way they have also explained. Suppose this is your memory, you can say this is main memory, or a larger memory. So from this memory, you can say multiple blocks here from this memory will be mapped to a single block in the single location of the direct map cache. So here you can say they have done the opposite thing. So for them this is the set and this is way. So they have just they did the reverse thing. So you can see these are the they have said the columns are their set numbers. So you can say here this is block, there are 4 blocks here. These 4 blocks are mapping to the same set here. So suppose if I say this is B1, this is B2, this is B3, and this is B4, then out of this B1, B2, B3, B4, only one block can be present in the cache memory at a time. So if suppose at this moment B1 is here, so now code is requesting for a word which belongs to B4, and then there will be miss for B4 in cache, right? So we'll go to main memory, we'll fetch B4, but we have to place it in the same location where B1 is here. So that is called conflict. So there is a conflict situation arises here. So we have to remove B1, and in place of B1 only we can place B4. No matter if there are free space available here, you cannot place it there because of the mapping policies. I hope you are understanding it. So that's why if we go for this is the direct map cache, right? So here in direct map cache, the chances of conflict is very high. So here It's many time it may be possible that when core is requesting for b1, after requesting b1, immediately core will go and request for a block called b2, but both b1 and b2 are conflicting in the same position. That situation may arise, but let us not discuss it in further detail. We'll discuss it when we'll discuss site associative cache. So at this moment, I hope you are understanding what is called direct map cache. If you understand what is called direct map cache, its structure, what is called set, what is way, what is called block, okay, what is how we are mapping it based on set index. If you understood this, then I think it is enough. Also, I hope you are understanding the concept of word block and block addresses and all. Those points will be important. Any of this point, if you think it is not clear, then you can ask me again, I will explain. So I see that there are some point I'll discuss here. See, there are tag. What is called tag, I have already explained. First part will be offset part, then remaining is set index. After this, whatever remains in your address is called tag. So if suppose this is your core and core is requesting for a word w2, okay, for this cache, then as I said, w2 is 2004. Suppose assume that the address is actually 64-bit address. So block is 2000. Okay, you can convert this as 64-bit address, right? No problem. So in here, every address you can divide into three parts. First part will be offset, second part is your set index, and remaining part is called tag. So that you have to understand what is called tag. Valid bit is required because if you have a cache memory, as I said, direct map cache, suppose this is your direct map cache, there are multiple sets here. So how can you find out that in this location if there is a valid data exist or not? So it means that you need to store a particular bit which will represent that, okay, this particular block is valid or not, means this location is empty or not. If this location is empty, then you can directly place a block. But suppose they are here at this moment, b1 is placed. So if you want to place another block in this location, that valid bit will be 1 here. So it means that there is a valid bit block already there. So first you have to remove this block, it back to main memory, and then you can store here another block. That's why a valid bit is important. Then I think let us go with the example here. So I've already designed a table. Suppose this is your direct map cache. So here there is only one entry. So you can say that this is the entry. Okay, this is the entry. There are multiple sets. There are 8 sets here. Each set is like this, but the content that will store in this set, I previously I said just will store a block b1 here, right? But when you store block b1, what are the content that will store in b1? First, obviously the data part. Data part means the actual content of this block that we fetch from memory, right? And that I said, suppose just I said 16 byte block we are considering. So if there is a miss, I'll go to main memory, I'll fetch a complete block, and that I'm calling it data of that block. Okay, size of 16 bytes. So obviously I'll store the data here. Obviously I'll store the data of this block, and with this I'll also store the tag part of this address that I'll store. Then I'll also store the valid bit. So these 3 things I normally need to store: valid bit, tag, and data. Okay, and for understanding purpose, I have also stored the index, but you can just understand that these are the numbering. So so now let us fill this cache one by one based on this request that is shown in the upper table. Let us go for the first request. Here the core is requesting for this block. So here I'm assuming this is the block address. Okay, assume that there is no concept of or you can say that each word size and block size are same. So block size is 4 bytes, suppose. So only one word. So I'm making it simple. So first time when it is requesting for 22, so this is the address. Instead of 64-bit address, here I am going with 5-bit address. So how many sets are here in this cache? This is my cache. So in this cache, how many sets are there? 8 sets. So how many bits are required for set? 3 bits are required for set. And remember, there is no offset required because there is only one word, right? Offset is not required. So I'm ignoring the part of offset to make it simple. So the first 3 bits will be for the set index. So in this case, 1011, the first 3 bit is 110. So the block is placing in this set 110. Okay. So 110. So what is the tag part? Tag part will be the last 2 bit. So tag part will be 10 here. This is the tag part. Now valid bit will be yes. Initially everything is no, no here. No, no, no. They are not valid. But now this is valid, and now we'll fetch the data, and data will be stored here. So data of this memory location. So data of this memory location is stored here. So initial, so when we do this at this time, this is let us count the number of miss and number of hit. So number of miss will be 1 here. Now let us go to next line. Next line is requesting for a address called 26. So 26 is 11010. So 11010, last 3 bit is 010. So this block is mapping in set number this 010 in this set. Okay. So in this set, you check the valid bit first. Valid bit is no. So it means that the set is the line is empty, and the block is also not here. So the number of miss will be 2 now. So now we'll fetch this block and store it here. So this will be yes now, and tag bit will be 11. Okay, and data will be stored here. Data I'm storing a data from this memory location. Okay. Now the third request is again for 22. So if you again you are it is requesting for 22, then you can say 22 request data is already there in the cache, right? Because we have fetched it in the first attempt. But how we'll check it? To check it, what we'll do, again, you concentrate on this address. First, you will find out the set index. Set index will be the first 3 bit, right? 110. So 110 means I'll concentrate on the particular set of 110. This is 110. Set is fixed. Then in this set, as I said, multiple blocks can be present, right? How can you sure that currently the block number 22 is present in set? That you can do by comparing the tag part. What are the tag you have stored here? Tag stored currently is 10. And what will be the tag of the third request? Here, if you go, the tag is 10. So 1010, there will be a tag match. The moment there will be a tag match, you can say that okay, the block number 22 is exist in the cache. There is a cache hit. So number of cache hit will be 1 here. Now, if I go to the next line here, line number 26, next block 26, then it is 11011. So 11011 means what will be the set address? Set index is 010. So 010 means this set, 010. Now concentrate on this set. First of all, you find out that whether the block will be hit or miss. What will be the tag here? Tag here is 01. Tag is 11, right? So 11, there will be a tag match here. So again, there will be a hit. So there are 2 hits here. So you can see they have written also hit. Okay. Ignore this 5.9b. They have written some table. That's why they have written 5.9. There are some tables after this page. That's why they have written like this. Okay. So now let us go to block number 16. So when you go to block number 16 here, then this set index will be 000. So it is this set. Okay, and the block is available? Obviously not, because valid bit is no. This is one way to check that this block is not in the cache. Another way to compare the tag. There is no point to compare the tag here because the block is not there at all. So what we'll do, there will be miss here. So number of miss will be 3. So let us put the block here, and the tag part will be 10, and data will be data from 1000. Okay, the next is they are requesting for 3. If they request for 3, then where it will go? It will go to 011. Okay, and no, I'll go with one more. I'll go with last one now. This one, 18. If I go for 18, then 010, right? It is 010. Yes, I'll go with 18. If I go with 18, then what will be the set index? Set index will be 010. So which set I'll consider? I'll consider this set. I'll consider this set, right? In this set, the block number 18 should place. Now, first of all, we'll check whether the block is already present. What is the tag part? Tag part is 10. So there is a block already present in this set, right? Why? Because the valid bit is yes now, or valid bit is 1. So one block is already present. Now let us compare the tag. So the requesting block tag is 10, but the block that is present in the cache, that tag is 11. So there will be no tag match. If there is no tag is not matching, it means that there is a cache miss. Okay, so obviously there will be cache miss. I have to go to main memory and fetch block 18. But the problem here is where to place 18. The location where the block 18 is mapping in the cache, that location is in that location some other block is placed, right? So what to do now? So the question now here, first of all, we have to remove the current block from this set. We have to remove the current block, and in place of this, new block will be placed. Okay, so now the question is, can we directly remove a block? No. If we want to remove a block, then you have to check whether we have updated something or not. Why? Because when core request for a block, there will be two things, right? Load and store. When it is requesting for a load, it is just reading it, and when it is requesting for a block for storing something, it means that code is writing something. So if code is writing something, then first it will write in the cache memory only, isn't it? If you just understand the concept of store, it will first read in the data memory. What is that data memory? That data memory is your L1D cache, right? L1 data cache. So ultimately it is writing in the cache. So if there is a block which is written by the cache memory or written by the code and it is available in the cache, and now you want to remove it, can you directly remove it? No, you cannot directly remove it. If you directly remove, then maybe it's that important update is gone, right? Because so what you need to do in that case, you need to write the data back into main memory first of all, and then you can replace it with some new block. So in that case, this is called dirty block. So if there is the block is dirty or not, this is important. So we need actually one more bit, but that is not important here, so I'll discuss it tomorrow. Here now only valid or not valid here we are discussing, but actually one more bit is required. It's called dirty bit. The dirty bit will understand that okay, that this block is now dirty, so before removing it from the cache, we have to write it back to the main memory, and then only that place can be free for other blocks. So I'll not explain this table anymore. You can understand the table by yourself also. So the table that I have made here, this same table they have designed here sequentially one by one, and this IDs they have written here. See, if you go here, see they have written 5.9F, 5.9D. So these are that's 5.9F, 5.9D like this. So you can understand it by yourself also. So my main intention here to explain you how a cache memory works. So but here I am using a simplified diagram. First I've explained you a word and block concept, but while I was discussing this example, I was assuming only word. I am not discussing about blocks and all. So this is a simplified diagram of cache memory, of direct map cache only. You can see this is the 64-bit address that every time, as I said, core will request for a word, right? So either it is W1 or W2, that address is a 64-bit address. Every address byte, every address is a 64-bit address. So if this is your 64-bit address, then first part is your byte offset. Okay, then next part is your set index. So from this set index, you can see we are first deciding a particular set here. Okay, and from this particular set, see the tag information will be available here, and this is a comparator. And with this comparator, the tag part of this requesting block will come here, and this will be compared here, that if there is a tag match here, then it is hit. Okay, and if there is no tag match, then it is a miss. Okay, and you can see here at the same time when this line is coming here, it is it is making this tag data available here, as well as at the same time it is also making the data part available through this line. But this data part will be accepted or not depend on this hit or miss. If it is hit, then this data will be directly sent to the cache to the core. If this is miss, then this data will not send, because this is not the correct data, right? So we have to stop it, and we have to do the other thing. Other thing means either we have to go to the main memory, fetch the data, and place the new data here. And doing this, if we need to replace the existing data, then first we have to do that. We have to replace the existing block that is currently stored here. So this is the simplified diagram of a direct map cache here. Here we are assuming only 1 watt per block. Okay, so you have to understand this diagram. This diagram will be very important. I will use it in my remaining lectures also. Offset and then tag index. Tag index is set index is very important. Based on this set index, the information of this particular set will be available, and this comparator will compare the tag part and the tag of the requesting address. And if this is hit, this matches, then we'll consider it a hit, and the data will be available through this line. Data will be available through this line in case of miss also, but in that case we should not accept this data because there was a tag mismatch. So this you can read. There are some explanation given here. I think you will easily understand those. I am not explaining it. So see, there are two problems, numerical problems here. Try to understand it by yourself. I hope you will understand it because I've already explained you the concept of block and words. So I was expecting to go a little further, but I think I have to stop here because there is no time is not permitting me. So from next lecture, I'll start from here. I need 10 more minutes to complete the direct map cache, and then I'll start with the new concept that is called set associative cache. Okay, so I'm stopping here. If you have any doubt, you can ask me now. So if you don't have any doubt, then you can